Ever stop to think about how a platform like Twitter or Facebook manages to give a totally unique name to every single tweet, every like, every comment? We're talking billions and billions of actions happening all over the globe, all at once. It's one of the most fundamental and, frankly, fascinating challenges in modern tech. So let's dive right in.
So here's the core problem we're trying to solve. You've got thousands of servers, right? They're all working in parallel. How do you make sure every single one of them can generate a unique ID for every single action without them bumping into each other? If two servers spit out the same ID for two different things, that's a recipe for disaster. And you can't have them all constantly checking in with the central boss. That would grind the whole system to a halt.
You know, the old school way of doing this, just using a simple auto-increment number from a single database, that's a complete non-starter in a big distributed system. That one database instantly becomes a massive bottleneck. Every single server has to get in line, waiting its turn to ask for a new number, and even worse, if that one database goes down, poof, your entire system is dead in the water. It's a classic single point of failure.
Okay, so engineers, being clever folks, came up with a few ways to tackle this. Let's look at the three most common first stabs at the problem. And as you'll see, each one, while smart in its own way, came with a pretty big gotcha.
So, the first idea is what we call multi-master replication. The logic is simple enough. You give each database server its own turf to play on. You might tell server A, hey, you're in charge of all the IDs from 1 to 1,000. Server B gets the next block, from 1,001 to 2,000, and so on. They each work in their own little sandbox and then just tell everyone else what they did.
Now, this sounds pretty easy to set up at first, right? But the problems start piling up fast. I mean, what happens when you need to add a new server? You have to go back and rejigger all the ranges for everybody. And you're always living with this risk of ID collisions, especially if there are network delays. It doesn't scale. Not for a system that's writing tons of new data all the time.
All right, next up, the UUID. So attempt number 2 takes a completely different route. We've got the Universally Unique Identifier, or UUID. The idea here is to forget coordination altogether. Every single server just generates its own gigantic 128-bit random number. And I mean gigantic. The number is so big that the odds of two servers ever generating the same one are basically zero. It's total independence.
And this is great, right? It totally solves the coordination problem. But, and it's a big but, it creates a whole new headache. Because these IDs are essentially random, they have no natural order. You can't just sort them to see what was created first. Imagine trying to build a Twitter feed where the tweets are all jumbled up chronologically. It's a deal breaker. Not to mention, they're long, ugly, and totally unreadable by a human.
So that brings us to our third approach, the ticket server. This is kind of like swinging the pendulum all the way back. It's like we're saying, okay, that one database idea wasn't so bad, let's just make it super simple. So you have one server, and its only job, its entire purpose in life, is to hand out numbers in order. Just like taking a ticket at the deli counter. Now serving number 57.
And hey, this works. We get our nice, clean, sortable numbers back. It's simple, but you see where this is going, right? We've just recreated that dreaded single point of failure. If that one little ticket server goes down, the whole operation comes to a grinding halt. We're right back where we started.
So let's lay it all out. When you look at them side by side, you can really see the trade-offs. Multi-master is risky. UUIDs aren't sortable. Ticket servers have a single point of failure. It feels like you can't have it all. We want something that's unique, sortable, scalable, and fault-tolerant. Are we just asking for too much?
Well, turns out the answer is no. You're not asking for too much. And that brings us to the big breakthrough. An absolutely brilliant solution that came out of Twitter, born from their need to handle mind-boggling scale. It's called Snowflake.
The real genius of Snowflake is how it packs everything you need into a single, compact, 64-bit number. It manages to encode the time it was created, where it was created, and a sequence number. And it does all of this without servers ever having to talk to each other. It's the best of both worlds. You get the independence of a UUID, but with the sortability of a simple number.
So how on earth does it do that? Let's pop the hood and take a look at the anatomy of a Snowflake ID. We're going to break it down piece by piece, and you'll see it's actually incredibly clever. Okay, so here's the blueprint. That first bit, don't worry about it. It's just a sign bit, always set to 0 to keep the number positive. Now the next 41 bits, this is the magic ingredient. It's a timestamp, measured in milliseconds from a specific start date. This is what makes every ID sortable by time, right out of the box. Then you've got 5 bits for a data center ID,
and another 5 bits for a machine ID. Think of this as the ID's address. It tells you exactly which server on the planet made it. And that last little piece, the final 12 bits, that's a sequence number. It's a tiny counter that resets every millisecond, and it lets a single machine pump out over 4,000 unique IDs in the same millisecond. Incredible. Now, here's a fun little piece of trivia about that 41-bit timestamp. It has a shelf life. With 41 bits, you can count up to a certain number of milliseconds, right? Well, it turns out that from whatever start date you pick, that gives the whole system a lifespan of, wait for it, about 69 years. Then the clock runs out.
So when you put all those pieces together, what do you get? What makes this approach so dominant that it's been adopted all over the industry? Let's just quickly recap the big advantages.
It's simple, really. Snowflake just flat out wins because it ticks all the boxes we were looking for. Uniqueness? Guaranteed, thanks to that machine and data center address. Time sortable? Absolutely. That's the whole point of the timestamp. Highly scalable? Yep, every machine does its own thing. And fault tolerant? For sure, because it's completely decentralized. There's no single point of failure. It just works. And that really is the fundamental difference. All the old ways forced you to choose. You could have sortability, or you could have scalability, but you couldn't get both in one package. The Snowflake way breaks that trade-off. It gives you everything you need in one elegant 64-bit solution. So Snowflake is an amazing solution for a super complex problem in distributed systems. But it does leave us with one last, really interesting question to chew on. That 69-year clock, it's ticking. So what happens when it overflows? What does the next generation of unique IDs look like? That's the next big challenge, something to think about.